Hi, I'm George Hammond, conference producer at Technology Networks, and I'm here to introduce our next talk, Beyond Materials, the Crucial Role of Battery Innovation in Accelerating Energy Solutions. I'm incredibly pleased to welcome Dania Ghantous. Dania is the co-founder and VP of Technology at Qnovo, the market leader in enabling software-defined batteries. She has over 25 years of experience in technology development related to materials, batteries, and computation algorithms. A battery scientist at heart, Dania's innovations and unique understanding of lithium-ion batteries enables her to recognize the theoretical promise of new materials and technology, yet distill it into practical implementations that can be readily commercialized. A very warm welcome to you, Dania. Following the presentation, we will also have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. And now, without further ado, I will hand over to Dania to begin her presentation.
Thank you, George. Thank you actually to Technology Networks for inviting Qnovo to this presentation. I'm excited to be here to talk about really the crucial role of adding battery intelligence in order to accelerate battery development and energy solutions. And what I'll cover today is really about why software, and more importantly, why adding intelligence is really essential for next generation battery management systems. We'll go through why it's important to monitor a battery really from the time it leaves the factory until the time it's ready to be recycled. And we'll also discuss how managing that battery really from its birth enables it to have a second life and potentially a third life, and how all of this really impacts the environment and sustainability. So let's start out with energy density. Energy density is a very important metric in battery development and something that has been pursued for many, many years. How do you increase the energy density of a battery? And I'm sure many have seen press releases about companies that are developing materials or even battery technologies that enable or have inherently high energy density. But why is it so important? And that's a really important question. So energy density is really about the ability to store more energy in a smaller volume. And it's important when it comes to applications that require many batteries to be assembled in a pack. So for example, in electric vehicles, a pack is made out of hundreds of smaller cells. So if a cell has higher energy density, meaning more can be stored in that smaller volume, then that pack does not require as many batteries and can actually be lighter. So when it's lighter, not only that reduces the overall cost of the pack, but it also makes the vehicle more efficient. And this is why energy density has been pursued for many, many years. So if we look today and we think about, well, how do you get to high energy density? The easiest way to do that is really to look at materials that have inherently higher energy density. So materials that such as solid state materials, or materials that use silicon anodes, or materials that use lithium metal as anodes, or higher voltage systems. And those are really great. However, that development takes a long time to go from the lab all the way to full-scale manufacturing. And at the same time, if we look at the market and we look at the different applications, the requirements are increasing. There's more demand on that battery. And so this advances in materials development alone cannot keep up with the market requirements. And at the same time, the market is pushing for lower and lower cost. So it becomes very difficult to just say, oh, we'll just make a higher energy density material, and that's how we'll solve the energy density problem. There are other options to increasing energy density, such as, increasing the active loading in a battery, or increasing the voltage range of the battery, designing the battery to operate at higher voltages. And while those can increase the energy density, they do compromise performance and they do compromise safety. And this is a lesson to learn from the consumer industry, where lithium cobalt oxide, the chemistry that launched the first lithium-ion battery more than 30 years ago, that's the path that chemistry has taken. This is the same chemistry that powers today's smartphones and laptops and iPads. That chemistry really increased the energy density initially by manufacturing improvements, but later on by really increasing the voltage of the system and giving it a higher energy density. But that really pushes the cell right at its right on the edge of a cliff. So what happens now is the chemistries that we use today, the nickel-based chemistries like NCM and NCA, and the phosphate chemistries like LFP, those are the chemistry of choice really for the foreseeable future. They are not going to go away. There'll be improvements to them, but this is what we have for the foreseeable future. And that's why it's important to understand why this metric of energy density is really important in battery development, and how do we now take these existing systems and expand their performance envelope in order to meet the demanding requirements of the industry. Now, at the same time, on the cell design aspect and the pack architectures, there have been some new innovations that have taken place. So for example, looking at the shortcomings of some of these cell chemistries, what can be done on the pack side in order to improve the performance of the pack, in order to improve efficiency, in order to lower cost. So one approach actually combines mixed chemistries. So taking chemistry, one can be more for power applications and one can be more for energy applications, and combining them in the same pack to improve performance. Another approach is really when the cells are assembled into a pack, it requires a lot of interconnects to be able to add these cells in the pack. But one approach would be to really reduce that and just and then add the cells directly in a pack and not assemble them in kind of smaller modules. So that improves the packing efficiency and it reduces cost. And as now we look at this combination of materials and we look at the combination of cell technologies and we look across at what we have today, and we have to look at these across different metrics from performance, energy density, power density, aging, self-discharge of a battery. We'll have to look at safety, how a battery operates at different conditions. And then at cost, what is the cost value of the cell, especially as you scale it to full-scale production? And as we look at this today, there really is no perfect solution. In cases where cost is good, in cases where performance is good in terms of energy density and power density, there's a trade-off when it comes to safety. There's a trade-off when it comes to cost. And so there really is no perfect solution today. And ideally, when we look at this chart, it should be just blue and green for all these different materials, but it's not. And this is the drawback of just relying on the materials performance alone. So this really points again that a different approach is required to be able to expand that performance envelope, to be able to meet the criteria of performance and safety and cost. Now, when we look at battery manufacturing, well, battery defects are really part of building a battery. And there's no way to avoid it. Battery manufacturing is still evolving, and we have seen that even when multiple batteries are produced on the same day, on the same line, no two cells are alike. So there will be variances between cells, and it's very hard to control these types of defects. Now, some defects can be detected before the battery leaves the factory, but most defects cannot be detected. Defects such as uneven coating or misaligned electrodes, or if there's a separator that has a folded edge. These cannot be detected before the battery leaves the factory. And so what happens is, under a combination of conditions of, operating conditions, environmental conditions, aging, these latent defects can lead to a catastrophic failure. They can actually lead to a big fire. And so safety is really, really important when we look at battery manufacturing. In fact, I think safety is more important than just focusing on performance. And so we can look at, adding better manufacturing practices. We can look at developing safer materials, but we have to keep in mind that those are not enough, because not only is the industry moving towards reducing cost, but these take a long time to be implemented or developed. So again, this points to the need for another solution. And we've seen the effect of these battery manufacturing defects. Safety at the end of the day is really not a compromise. As I've said, to me, it's more important than just focusing on performance. And if we look at systems like electric vehicles, where you have hundreds of cells that are used in the same packs, or you look at energy storage, where you have hundreds and thousands of cells that are used, in these large containers, these manufacturing defects can have catastrophic outcomes. So how do we control this? How do we handle these billion-dollar recalls for these batteries and contain them? How do we enable having less recalls like that? Because not only do they affect, not only are they costly, but remember, every time there's a recall and you have to replace the batteries, you also have to produce more batteries, and producing more batteries requires time. And then you don't know if you solved the problem that caused it in the first time. So again, this points to the need for having a different, another approach to, and not just relying on the battery materials alone. So when it comes to performance, so when it comes to optimizing battery, and this is what battery developers that have spent a long time doing, how do you optimize for performance and safety and cost? But all of these have to work together in order to manage how that battery is aging. So if you're asking for high energy density or high power density, or the ability to do fast charging, well, how do you make sure that this doesn't impact your safety? At the same time, if you're looking at reducing cost, how do you enable a cost reduction without impacting performance or safety? For example, if you use lower cost materials, or if you use lower cost components, how do you enable that these lower cost materials are not going to impact safety? So this is a very hard problem to solve. And again, it all needs to be focused on how that battery is aging. And that is why materials alone materials alone are not sufficient. Cell technologies alone are not sufficient. And that's why these advances in battery development have to be complemented with intelligence. And that intelligence comes into the form of software. So let me tell you a little bit about how we do it. So, recognizing this problem, it really comes down to, how do you add intelligence to the battery management system? And this is where what we've developed at Qnovo. We have our intelligent algorithms that really sit as an additional layer on top of standard battery management systems. And that has enabled us to really expand that performance envelope and look at performance and cost and safety. And we've been able to do that across different verticals. We started on the consumer side, on the smartphone side, where we've shipped 150 million smartphones with our software. And now we're on looking at mobility applications, electric vehicles, and fleets and electric trucks, as well as energy storage, and expanding the performance envelope of these systems as well. And we've developed this over more than 13 years now, and we're globally recognized across the industry. And we work closely with our customers, with our partners, and with our investors. And we've been, we really over these years, we really have a very deep knowledge in terms of how batteries age. And how to mitigate that aging, and then implement that in software. So the approach that we've taken is really by using computation algorithms with our battery models to measure degradation in real time. And this is really important, and honestly, it has not been done before. And what the fundamental innovations here center around two pieces. The first one is about the method. We've put together the methodology to use electrochemical impedance spectroscopy in software. So that way we can measure the chemical processes, and we can measure them in real time, and we can measure them all the time as long as we can sense, as long as the software can sense the battery. The second big part of the innovation is really around being able to do closed loop optimization to mitigate degradation. And this is an important part in the foundation of our software. Closed loop optimization is necessary because, as I mentioned before, in battery manufacturing, no two cells are ever alike. And so a closed loop allows that harmonization of performance. And so these are the two core pieces of the innovation. But with those, we built 4 separate functions that really serve as the foundation, and they guide the development, and they guide the evolution of our algorithms. And so in sensing, we are able to simulate the battery and make the requisite measurements. And then these measurements don't really mean anything if you can't interpret what they mean. So this is where the models come in, and being able to interpret these measures. And these are, multiple different types of models that can interpret these measurements and then determine, how is the battery aging? Is the battery aging because it's aging normally, or is the battery aging faster due to whether the presence of a defect or any other case? And those models then allow us to predict, where is the battery going? What is the future performance of that battery? And once we know that, then we can go back and close the loop on the charging parameters. And this is a process that occurs throughout the entire charge process and throughout every single charge process. And so with that, we are able to gather a lot of information about the battery, and we have the historical profile of how that battery is aging. And so we've been able to do this across multiple chemistries, multiple vendors, multiple applications, and this is really the foundation of the software. Now, in order to build that, there are certain building blocks that are necessary in building intelligent software, and it really focuses on 3 main parts. The first one is about models. Models are really important because we need to understand how a battery ages, how it fails under different conditions, how does it vary from cell to cell? How does it vary across vendors? So those models become pretty comprehensive, and we use a variety of different models to be able to understand how the battery is aging. And so we can develop that aging model relatively quickly because of the knowledge and the data that we have. The second part is really around data. We are measuring data. We are making measurements all the time, as long as the software is on, as long as charging is taking place. So by being able to measure the software, we generate a lot of data. And so that data really helps us to go back and optimize our models. And that data is not just data from a lab, but it's also field data. It's coming from the field to tell us, hey, under different use cases, this is how the battery is functioning. So all of these help our models to continuously evolve and learn from that data. But having the models is great, having the data is great, but if you can't do anything about it, then it doesn't really help. And that's where aging control comes into place. And that's why having the ability to control is really important. So these algorithms then use that data and use how the models have interpreted that data to determine how do you adjust the charging profile. And so as batteries age, their health starts to deteriorate. And so the charging has to adapt based on how that battery is aging. So these are really the key to having this intelligent software. The combination of these three is actually very powerful. And it really enables it really actually enables different features, from improved performance to improved safety to enabling second life applications. So now let's go back and talk a little bit about safety. Safety is really critical for large battery systems, especially in cases in situations where more cells are required within a pack. And large battery systems for energy storage, for example, require a lot of cells to be assembled together. And so how do you determine safety today? Well, there really isn't a perfect solution. Actually, there isn't a solution. Today, we rely on making measurements of capacity or making measurements of resistance to monitor if something went wrong in the battery pack. But capacity is a good measurement and resistance is a good measurements, but they're not instantaneous measurements. And so they become more like lagging indicators as opposed to instantaneous measurements to determine if something is going wrong in the cell. So because they're lagging indicators, they will only change, or you will see that change at a much slower time constant, as opposed to looking at something really that's an instantaneous measurement. So if we bring it back to where does software fit into this? Well, that software intelligence can provide really more insights on the data that's collected, and it can look at that measured data and say, hey, is the battery aging normally or is the battery aging abnormally? And there's a big distinction between normal and abnormal aging. So for example, if you have two cells that have exactly the same capacity, but one is aging normally just through regular wear and tear, while another one is aging because there is the presence of a defect that is slowly that it's increasing the aging. You can't really tell by just looking at capacity. You need to have different indicators. And with software and being able to continuously monitor the battery, then you're able to detect these changes much sooner, so that these early indicators can become it can be monitored and flagged. And when we look at large battery systems, how do large battery systems today handle predictive maintenance? And so in these large applications, the way predictive maintenance is done, it's more time-based. And so, after a period of time, some of the batteries are swapped out, but they're swapped out maybe because their capacity is a little bit lower, but you don't know if the remaining ones have a defective battery in there. So the process is not very, it's a little bit broken in that sense. But this is where software can help, because not only it can help detect if there is a defective cell, but it can also enable a different approach of doing this, where it can really measure it on the pack, which makes it not only as a faster process, but actually it becomes more economical. So that's something to keep in mind as we look at deployment of large battery systems. The solutions that exist today are inefficient, and we need to look outside of that, and we need to look at software innovation. Now, when we look at battery intelligence, so what does battery intelligence do? Well, what it does is it controls and mitigates degradation. And by controlling and mitigating degradation when the battery is in its first life, it really opens up the door for applications in a second life, whether they go into energy storage or other application. Controlling that degradation is really key. So when we look at the charging side, today, if you look at charging, I mean, charging, the way batteries are charged today is actually, it makes them degrade faster because the standard charging really does not take into account what the battery state of health is. It will always charge it the same way, regardless of the battery state of health. And as a result, it starts to accelerate the damage in the battery. And by doing that, you start to see a lot of variation in the performance of the cells. When you look at intelligent charging is more about how do I charge the battery based on its state of health, based on the use case that it's in, based on the environmental conditions that it's in, based on the operating conditions. And it's a very dynamic and adaptive charging that takes into account what that battery's age is, and it charges us according to the battery's age. And so as a result of that, you can mitigate and slow down that degradation, and then it opens up a set of performance features. So when we look at these different performance features from intelligent charging, they've really addressed and look at kind of addressing that triangle that I showed earlier with the performance and safety and cost. So fast charging has been in the news for a long time, especially when it's for electric vehicles, is how fast can you charge the car? But fast charging alone is not just a requirement. Fast charging cannot come at the expense of compromising performance, cannot come at the expense of compromising cost. And so when we look at that, and safety, of course. And so with intelligent charging, you can enable that fast charging while maintaining performance because you're constantly monitoring and mitigating the degradation that can happen. And then the battery stays safe because you're constantly monitoring that battery and you know where and how to charge that battery and keeping it away from conditions where the battery can get into some safety issues. But then when we look at lifetime extension, lifetime extension is so important because lifetime extension, extending the life of a battery, especially for an electric vehicle, not only reduces cost, but it helps the environment. And so with intelligent charging, because you're mitigating that degradation, you can actually increase the lifetime of that battery. But at the same time, because it's an adaptive and dynamic charging, it actually harmonizes the performance of all of the cells. So regardless of what their variations are, in order to mitigate and get similar performance. When you look at standard charging, because it's almost like a one size fits all, so you're constantly charging the battery exactly the same way, regardless of what the battery state of health is, you see a lot of variation in performance. And that's one of the drawbacks, or one of the many drawbacks of standard charging. Also, with battery intelligence, we can unlock and access additional capacity in the battery. So if you look at batteries today, especially in electric vehicles, you're not really using the full battery. You're only using maybe 80 to 90% of it. But you can still access that. So you're paying for a full battery, but you're not using all of it. And so being able to access additional battery, additional of that reserve capacity in the battery also opens up a lot of opportunities, because now, again, you don't need as many batteries. And then you can reduce costs because you're not using as many batteries. So being able to do that, with intelligent charging allows you to kind of expand on that, on accessing that extra capacity, really without compromising performance and without compromising safety as well. Okay, and so when we look at battery intelligence, um, when we look at how it improves cost and how it improves environment. So as I mentioned before, being able to control and monitor the battery and mitigate the degradation enables the battery to have a longer lifetime. And so this is really important when it comes to the environment and when it comes to sustainability. What happens to the environment? Like, what happens to the environment if we can increase the battery lifetime just by 1 year? What happens to the environment if we can reduce the recalls due to safety defects? What happens to the environment if we can, expand and access that extra capacity in the battery just by 5%? So if we look at the cumulative effect of doing these over time, we can reduce about 250 million metric tons of CO2 becomes possible. And just to kind of put it a little bit in perspective, 10 million metric tons is the equivalent of about 2 million cars per year. So you can kind of do the math to see how you get to 250 million metric tons. But the point here is battery intelligence allows for this extension in the lifetime of the battery, and by allowing it to extend it really just by 1 year has absolutely massive impact on the environment. And so we have to keep this in mind, because as the electric vehicle market continues to increase, we will see more and more cars. And so being able to really make these cars last longer has a huge impact on the environment. Okay, and so again, being able to monitor and control the degradation of the battery, really from the time it leaves the factory, really enables better control in how the battery ages. So, for example, being able to manage the battery through its first life allows it to have a second life or even a third life. And in electric vehicles, when a battery reaches end of life, it still has, 70 to 80% of its initial capacity is still remaining. But if you have been using this battery in an uncontrolled way, meaning it has not, you don't have that battery intelligence in the battery management system, then it becomes that performance after 70 to 80% of the initial capacity is reached, you really don't know how reliable that battery is going to be, because you don't know how it has aged. You don't have you don't really have an idea what that battery has been through. And so with software, especially when you look at reuse applications for energy storage, with software being able to monitor that battery, you know exactly how that battery has aged, and you know exactly what it has been through, because you're continuously collecting that data and you have that historical profile of how that battery aged. So when it gets to 70 or 80% of its remaining capacity, of its initial capacity, then you can decide, are these batteries suitable to be reused or recycled? And so Um, and each one plays a different role. So from the reuse side, when we look at today, how do you even figure out how to reuse these batteries? And so looking at capacity and looking at resistance is one method to do that, but this is not it's a method that takes a long time, and it's not very economical because you have to go through every single battery that's in a pack to be able to understand how that battery, what the battery health is in order to assess that battery health. But when you look at it from a software standpoint, where you've been continuously monitoring these packs and you have the state of health really of every single series element that's in that pack, you can immediately rank the batteries based on their state of health. You can rank them from least healthy to most healthy. And then it becomes easier to regroup them in a much more economic. You can do this at the pack level. You don't have to disassemble the pack in order to be able to kind of sort and rank the cells. But once you can sort them and rank them, then you can say, okay, well, these cells or these series elements will go into one group, and then you can bin them according to their state of health. So this is an important part at looking at how we enable Second Life applications. At the same time, when we look at recycling, sometimes when batteries have been exposed to different type of damage, then the batteries can have, for example, lithium plating. And when lithium plating is present, it becomes harder for these materials to be recycled and recovered. But when the batteries are controlled, then you're able to manage what type of degradation is taking place on these batteries, and then it becomes easier to recycle the batteries, so you kind of recoup it. So from that standpoint, not only can you enable Second Life applications, but you can also enable that circular economy. So with that, I conclude my presentation. But what I'd like to leave you with is, software changes everything when it comes to batteries. And it doesn't matter what the material is, and it doesn't matter what the cell form factor is, and it doesn't even matter what the application is. Software is really, really essential to advances in batteries, as well as advances in systems. And all of these applications, especially with this onset of this electrification effort, all of these applications require the use of software and require really a different approach than what we're doing today, which is just relying on materials and the battery vendors to improve performance. Thank you.
Thank you so much, Dania. That was a fantastic talk. As with all the other talks in the event, we're likely going to have lots of questions from the audience. I can see that we've received some already, so I'll move straight onto the Q&A now. Your first question is, what role will Second Life batteries play in the future of energy storage?
That's a great question. Second life batteries really, first of all, let me redefine what second life batteries are. These are batteries that have been previously used, and in this case, they've been previously used for electric vehicle applications. And so, and by the time the batteries reach end of life, they still have 70 to 80% of their initial capacities are available. So being able to reuse them, has multiple benefits. So for one, it's more cost effective. So having that, reducing the cost really helps because it's not an additional. It's a battery that's already been used, so it's going to be much cheaper than buying a brand new battery pack. And because it's already used, you're actually helping the environment a little bit. So from a sustainability standpoint, it helps because you don't have to make new batteries to be able to use them. But the thing to keep in mind is that when we get to second life batteries, it's important to understand how that battery aged. So if we don't have any idea how the battery is aged, then it becomes much harder to determine, can that battery go for second life applications? And so the premise right now is that, once EVs have reached their end of life, you can just take the batteries and put them for energy storage application. And it's not as easy as it sounds, because you do need that intermediate step of being able to figure out, how do you reuse these batteries, or how do you recycle them? And this is where software comes in and can help a lot.
That's fantastic. Thank you so much, Dania. And just to follow on from that, how can we ensure that second life batteries are used safely and responsibly?
Yeah, that's a great question. Again, it comes back to, how was the battery used in its first life, and understanding what the history, or what that battery has been through, really enables it to have a second life. And so, in order to do that, this comes back to, how do you sort those batteries? How do you assess their life? Do you have to disassemble every single pack, tear all the batteries out, and then test them separately? Or can this be done in an easier way, that's more cost effective and actually and much safer? So again, from the safety standpoint, understanding its first life is important, because you want to make sure that those batteries are reliable to go into a second life. And again, this is really, I keep bringing it back to software, but this is where software really helps in understand how these batteries have aged.
Another excellent answer. Thank you so much. Just quickly, to everyone in the audience, we will answer as many questions as we have time for. And to move on to our next question now, what are the technical and economic challenges of using second life batteries?
Yeah, I mean, the technical challenges, again, comes back to, how do you know this battery is reliable? If you don't know what the battery has been exposed to in its first life, it becomes very difficult to understand what it can do in its second life. And so this is where it becomes, this is from the technical side of it. The economic challenges is, how do you do it? How do you take all of these battery packs, disassemble the packs, and then sort them and group them and assess them, and then rebuild them again for energy storage applications? That is still being determined. And that's why you need an intermediate solution that can just take the pack and be able to make an assessment. Is this a good pack? Is this not a good pack? That way it becomes easier to at least sort them in terms of ones that can be reused and ones that can be recycled. So, this is still evolving. I don't think, this is not mainstream yet, but this is kind of where we're heading, is that we'll be able to take used batteries and then use them for second life applications.
That's wonderful. Thank you for explaining that for us, Dania. We have time for just a few more questions today. So moving on, what role will energy storage play in the future of electric vehicles?
Yeah, so for energy storage, I think if we look at, as the EV industry is increasing, it becomes important to be able um, to have a kind of efficient charging, and having efficient charging infrastructure becomes a key point. And so one of the areas where energy storage can help with is by integrating into charging stations, into EV charging stations. So that way you can actually you can have more EVs, and you're able to provide additional benefits. So not everything is being being connected to the grid at the same time. And so by leveraging the use of these energy storage systems, then you can operate some of these charging stations maybe more efficiently.
Thank you so much. And we have time for one final question today, which is, what are the latest developments in battery charging technology, and how can we optimize charging to improve battery life?
Yeah, that's a great question. Well, I think the latest developments are all about advanced algorithms in order to be able to, charge the battery as fast as possible, and extended cycle life. And it's really about understanding, comes back to understanding how that battery ages and how it ages under numerous conditions, under different use cases, and then being able to react very quickly and dynamically to adjust charging based on how a battery is aging. So you can slow down the degradation, but more importantly, it's about controlling the battery's aging and then making sure that the battery stays safe at all times. So again, this is where software plays a key role in taking existing chemistries and future chemistries and being able to unlock their performance and really expand on their performance envelope.
Thank you so much, Dania. Unfortunately, that is all that we have time for, but we are incredibly grateful for you being here today. Any questions that we didn't have time to get to will be sent to the speaker after the event. And as with all the other talks in the event, this talk will now be available to view whenever you want for the next 30 days. That just leaves me to say thank you once again, Dania, and we will be back soon with the next talk.